Hello students, hope all of you are well. So today we are going to discuss one of the most important topic of the Laplace transformation. We can say commonly this is one of the common question in every branches of engineering. We face in the exam, we face in the internal exam, we face in the city exam, semester exam. This is a common question, that is the solution of an ordinary differential equation, or precisely to say solution of a initial value problem using the Laplace transformation. So today we are going to discuss about this topic. So this topic we are not only going to discuss the solution of the initial value problem, but also within the problem we are going to learn how to solve the Laplace inverse transformation using the partial fraction method. Moreover, some typical formula and the properties of Laplace transformation we have to use. So basically the solution of an ordinary differential equation using Laplace transformation is nothing but a summary of the full Laplace transformation course. So let us start today's topic. So before we are going to start, we need to know the basic formulas for the Laplace transformation on the derivative. So suppose we are having a function f which is a real valued function, and also we need to understand the basic condition on which the Laplace transformation will work over the derivative. So suppose we are having the function f as well as f dash, both are real valued continuous function for t greater equals to 0, and there exists a positive real number m such that mod of ft, modulus of ft, must be less than m into e power lambda t, where lambda is also a positive constant. This condition is known as the exponential order of Laplace transformation. If any function satisfies this condition, it says that it is satisfying the condition of the exponential order. Then the function will have the Laplace transformation, that is the function is continuous or maybe piecewise continuous, along with it is having the exponential order, then it satisfies the sufficient condition of Laplace transformation, and Laplace transformation of the function f exists. Now if f and f dash both are continuous function along with this condition, then we can say if f double dash t is also piecewise continuous. Piecewise continuous means it is not fully continuous, there will be some break in the interval, so that each and every sub interval, within the each and every sub interval, the function f double dash is continuous. So we can have the Laplace transformation of f dash t and the Laplace transformation of f double dash t. And what is the formula that I have written here? Laplace transformation of f dash t, that can be formula written as s into capital F of s minus f of 0, small f of 0. This small f is nothing but the base function small f dash t. It is coming from small f, and this capital F is the transformation of small ft. What I have written here, that is Laplace transformation of small ft, is nothing but our capital F of s. Similarly, Laplace transformation of f double dash t will be a square into capital F of s, that is the transformed function, minus s into small f of 0, that is the function of time variable t, minus f double dash 0, that is also the function of time variable t. So s Laplace transformation of f double dash t is a square fs minus s into f of 0 minus f dash of 0. So with this we are going to solve the Laplace transformation problem. But before that, little description about what is an initial value problem and its example. So suppose we are having a differential equation which is prescribed with a condition, and where the condition is given in such a way that the dependent variable is defined at a specific point. Okay, such a condition is known as an initial condition. So suppose we are having a differential equation, definitely there will be dependent variable and independent variables. So the motive of this definition says that if we are having the dependent variable at a specific point, the conditions are given like this, then such a condition is known as the initial condition. Now if the differential equation comes only with this initial condition, no other condition is given, then the differential equation is known as the initial value problem, or in short we can say it as an IVP, initial value problem. So basically with the Laplace transformation we are going to solve this kind of initial value problem only. We are not going to solve boundary value problem. So suppose for your understanding, I have given three conditions based on one differential equation. ODE I have taken for your basic understanding, and to identify which is the initial condition when which is the boundary condition. So suppose we are having d2i dx2 plus px into dy dx plus qx into y equals to rx. So this is the given differential equation. Now the first condition is given as y of a equal to b and y dashed of a equal to c. So y is our dependent variable, y is given at a specific time a, y dashed is also given at the same time a, or same position or the same point a. So definitely y at a, y dashed at a are given. So this condition is nothing but our initial condition. Now let us come to the rest of the condition, that is y at b is given but y dashed at b. So here we can see the function is defined on two different positions, y at b, y dashed at b. So this is not an initial condition, this is said to be boundary condition. So let us come to the third one, y at a is given, y at b is given. So also here y is prescribed at two different points. So it is not a initial condition, it is a boundary condition. In our syllabus precisely we are having solution of Laplace transformation for initial value problem. Now let us come to the solution part, how to approach to this kind of solution. So we are having one differential equation d2i dx2 double derivative plus 6 into dy dx plus 8y equals to 2, where the conditions are given as y at 0 equals to 1, y dashed at 0 equal to 1. So what are the information you are having? It is a second order differential equation and it is an initial value problem, because y at a specific point and y dashed at the same point has been given to us. So we can apply the Laplace transformation to solve this kind of question. Now we have to take the Laplace transformation on both sides of the given equation. So L of y double dashed means double derivative of y. 6 is constant, using linearity property we can take 6 out and we can write down Laplace transformation of y dashed plus 8 into Laplace transformation of y equals to 2 into Laplace transformation of 1. Why is Laplace transformation of 1? Because with 2 nothing is there, so we consider that 2 is multiplied with 1 only on the right hand side. So Laplace transformation will go over 1 only. Now we consider that Laplace transformation of small y x equal to capital Y s. Y of s is the transformed function. So we have to apply the Laplace transformation and the given differential equation will turn into an algebraic equation which is easy to solve. Okay, so that is the advantage of the Laplace transformation. So we have to apply the formulas that I have written already for double derivative and single derivative. So what is the Laplace transformation of y double dashed? That is double differentiation. So the formula is a square into capital Y of s minus s into small y 0 minus y dashed of 0. So this is coming from the first Laplace transformation of y double dashed. Now we come to the second term, 6 into Laplace transformation of y dashed. So what is the term we will get? 6 into formula for Laplace transformation of first order derivative is s into capital Ys minus small y0 plus 8 into Laplace transformation of y is 8 into capital Ys, because we have considered Laplace transformation of small y equal to capital Y, and 2 into what will happen, Laplace transformation of 1 is 1 upon s. So right hand side we are having 2 upon s. Most of the time student make mistake, they forget to do the Laplace transformation on the right hand side. So from the beginning the question on the solution will become completely wrong. So be very careful while doing this kind of problem. Now what is the next step we have to do? In the given question already you will see that the two values will be prescribed. So here y at 0 equal to 1, y dashed at 0 equal to 1, both are been given. So we have to put this y0 equal to 1 and y dashed 0 equal to 1 and open the bracket. So what we get, a square into capital Ys minus s into y0 is 1 minus y dashed 0 minus 1 plus 6 into s into ys minus 6 into y0 equal to 1. So it will become minus 6 plus 8 into ys equal to 2 upon s. Now the next part that we have to take ys term common. So wherever we see ys, so these terms you have to take common and write down the rest of the term within a bracket. So if I take this ys term common, what I am getting, a square plus 6s plus 8. So I have written this coefficient of ys term. Now except this ys term, some more terms are there on the left hand side. So we have to take all these terms on the right hand side. So here minus 1 and plus minus 6, so it will become minus 7. So it will go on the right hand side, so it will become plus 7, and this minus s also it will go to the right hand side, so it will become plus s plus 7. So what we will get, capital Ys value, so we have to divide the right hand side by a square plus 6s plus 8. So what we are having here, that is 2 upon s, already it was there. So with that term we are having 2 upon s into a square plus 6s plus 8 plus s plus 7 by a square plus 6s plus 8. Before we go to apply the partial fraction method, always try to simplify it. So capital Ys will come after doing the LCM. We will get in the numerator a square plus 7s plus 2, and in the denominator if you notice we are having a square plus 6s plus 8. This term can be factorized using the middle term factor. So using the middle term factor we can have two terms here, that is s plus 4 into s plus 2. That is very simple to find out this middle term factor. You can definitely able to find out. So now we are going to apply the inverse Laplace transformation, because ys is not our desirable thing. We need small y. We have changed from small y to capital Y using the Laplace transformation. So we have to come back to small y again. So how to come back from capital Y to small y? We have to take the inverse Laplace transformation. So we have taken inverse Laplace transformation on left hand side. So we get small y on the left hand side. On the right hand side also, on this function we have to apply the Laplace inverse. Now before we go to do the Laplace inverse, we have to apply the partial fraction method. So here in the denominator we can see three terms are there, or three factors are there. Each and every factors are linear, and the highest power of s in the denominator is 3, while the highest power of s in the numerator is 2. So we can apply the first rule for the partial fraction, that is if we are having the linear factor, the partial fraction can be written in the following manner, that is a upon s plus b upon s plus 4 plus c upon s plus 2, single factor. Now we have to take the LCM, so we are having a square plus 7s plus 2 equals to a into these two terms, that is s plus 4 into s plus 2, plus b, since b is coming with s plus 4, so b will get multiplied with s and s plus 2, and with c, s plus 2 is already there in the denominator, so c will get multiplied with s and s plus 4. Now we have to put some values of s. These values we are putting randomly. There is no rule, because partial fraction is always identical, so you can put any arbitrary value, but to get your calculation more easily, from the factors itself we can select the values. So we put s equal to 0. From there, after calculating, we get the value of a as 1 by 4. Similarly, by putting s equal to minus 4, we get the value of b as minus 5 by 4, and putting the value of s equal to minus 2, we get the value of c, that is equals to plus 2. So ultimately what we are having, we have to substitute the a value, b value and c value in these factors. Okay, and we have to perform the Laplace inverse on both sides. So what is our final answer? Y of x equal to L inverse of a value is 1 by 4 upon s, L inverse of b value is minus 5 by 4 by s plus 4, c value is 2, so L inverse of 2 by s plus 2. All the constants we have to take outside of the Laplace inverse. So we are having 1 by 4 L inverse of 1 upon s, minus 5 by 4 L inverse of 1 by s plus 4, and 2 will taken outside, L inverse of 1 by s plus 2. So 1 by 4 L inverse of 1 by s. 1 by s L inverse is 1 itself, because Laplace transformation of 1 is 1 by s. So L inverse of 1 by s is going to be 1. In the last of this video, I have added all the formulas. From there you can take the snap and you can practice. So 1 by 4 it will come, minus 5 by 4, 1 by s plus 4, that is equals to e power minus 4t, and L inverse of 1 by s plus 2, it will be e power minus 2t. Why? What is the reason? Because L inverse of 1 upon s plus a, this value is e power minus at, and L inverse of 1 upon s minus a, this value is e power at. So here it is s plus 4, so we apply the first form, so it will come e power minus 4t, and s plus 2 it will come e power minus 2t. It is very easy to understand. So that is the answer. Now we come to the next problem to get it more clear idea. So here the problem is y double dashed minus 3y dashed minus 4y equal to 2 into e power minus t, where y of 0 equal to 1, y dashed of 0 equal to 1. So what we have to do? Same thing, we have to apply Laplace transformation on both sides of the given differential equation. So Laplace transformation of y double dashed 3 into Laplace transformation of y minus 4 into Laplace transformation of y equals to 2 into Laplace transformation of e power minus t. So we put Laplace transformation of small y equal to capital Y of s. So now we are going to apply the formula for the Laplace transformation, that is the double derivative formula and first order derivative formula. So Laplace transformation for y double dashed is a square capital Ys minus s into small y 0 minus small y dashed 0 minus 3 into s into capital Ys minus small y 0. It is the derivative formula for the first order derivative. This is the formula for the second order derivative. Minus 4 into capital Ys, because Laplace transformation of small y equal to capital Y. On the right hand side we have 2 into e power minus t, just now I have told you. So using that formula we can write down 1 by s plus 1. So what is our next task? Our next task will be that we have to substitute the value of y of 0 and y dashed of 0 and open the bracket. So y0 and y dashed 0 both are 1. So we have substituted the value. Now we are getting this one. Okay, so the next task is to take common the ys related term. So here one ys is there, here another, and here another. So we have to take all the ys term common. So we get in the left hand side a square minus 3s minus 4. Apart from this, the rest of the term you have to take it on the right hand side. So this minus s will go to plus s, minus 1 plus 3, so it will become plus 2. It will go on the right hand side, so it will become minus 2. So we have to divide this a square minus 3s minus 4 on the right hand side. So we get capital ys equal to 2 upon s plus 1 into a square minus 3s minus 4 plus s by 2 upon a square minus 3s minus 4. So we have to just make a middle term factor of a square minus 3s minus 4, and it is coming as s minus 4 s plus 1. Simple middle term factorization we have done. S minus 4 s plus 1. We have done the LCM of these two quantity, and after simplification 1 or 2 step, you can see that the final capital ys value is coming as a square minus s is in the numerator, while in the denominator we are having s plus 1 2 terms it is coming. So s plus 1 whole square into s minus 4. Now capital ys is not our required solution. We need small y. How to get small y? We have to take the inverse Laplace transformation. So we have taken the inverse Laplace transformation over capital Y. So it is coming small yt equals to L inverse of a square minus s by s plus 1 whole square into s minus 4. What is the difference between this one and the previous one? Because here we are having the factors in the denominator which is a repeated factor. So here we have to apply the formula number 2 of the partial fraction, where the factors are going to be repeated more than one time. So how to write down this partial fraction? That is a by single factor, that is s minus 4. Now we have to start with the repeated factor. So b by s plus 1 by plus c by s plus 1 whole square. Suppose we are having s plus 1 whole cube here. So what will be the next factor? Plus d by s plus 1 whole cube. So whatever the power will be in the repeated factor, up to that term we have to write down in the partial fraction. So the previous problem, that the rule we have used, that is the rule number 1. Here we have applied the rule number 2. Now how to get the values for a, b, c? This is very simple. We have to just cross multiply or do the LCM. So a square minus s will come on the left hand side. On the right hand side we get a into s plus 1 whole square plus b into s plus 1 s minus 4 plus c into s minus 4. Now we have to substitute the value of s. For our easy calculation, we have put s equal to minus 1, which will give us the value of c as minus 2 by 5, s equal to plus 4, which will give us the value of a equal to 12 by 25, and s equals to 0, which is giving us the value b equal to 13 by 25. Okay, so we have to substitute all these a, b, c values here. So ultimately what is coming as a result? So yt is coming as L inverse of 12 by 25 by s plus minus 4 plus 13 by 25 by s plus 1 minus 2 by 5 by s plus 1 whole square. So all the constant terms we have taken outside because of the linearity property. Okay, and inside the s related terms we have kept. So L inverse of 1 by s minus 4, it is e power plus 4t. 1 by s plus 1, it will be e power minus t. Just in the problem 1 I have described the formula. Now let us come to understand this case. 1 by s plus 1 whole square, it is not coming from any one of the formula. So here we have to apply the knowledge of the first shifting property of the Laplace transformation. So what first shifting property says? Suppose Laplace transformation of small ft, that is equal to capital Fs. Now we want to find out Laplace transformation of e power at multiplied with ft, then the result will become f of s minus a. Every s will be replaced by s minus a, that I have written here. That is e power minus t at ft, that is equal to f of s minus a. Now if you take Laplace inverse of f of s minus a, that is in the fs term, if we see any kind of terms are there which is coming as s minus a related term, s plus 1 whole square, s minus 1 whole square, s minus 1 whole square plus 1, this type of term is there, then what we can do from there, first of all e power at is going to common from that term, and rest of the term will be L inverse of f of s. So if we look at this particular term, s 1 by s plus 1 whole square, so s is replaced by basically s plus 1, right? So s is replaced by s plus 1. So if we compare with f of s minus a with 1 by s plus 1 whole square, then a value is coming as minus 1. So as per the rule, e power minus t should come outside using the first shifting property. So if we take e power minus t outside, it will be L inverse of fs. Now there is no s minus a, so since minus 1 is going outside, it will become 1 by a square only. So it will becoming L inverse of 1 upon a square. So L inverse of 1 by a square is nothing but just t, because L of t is 1 by a square. So L inverse of 1 by a square will be t only. So here we are applying the first shifting property to get down the result. Okay, so now we are going to come to last problem for our discussion. So here we are having y double dashed plus 4y dashed plus 3y equal to 10 into sine t, where y of 0 equals to 0 and y dashed 0 and y dashed 0 y0 equals to 0, y dashed 0 equal to 0, both are 0 basically. Okay, so let us quickly now try to recall all the formulas. So Laplace transformation of y double dashed, we have to take Laplace transformation of on both side of equation. So we have Laplace transformation of y double dashed 4 into L of y dashed plus 3 into L of y equal to 10 into Laplace transformation of sine t. Now we have to apply the formula for double derivative, that is a square into capital Y minus s into small y0 minus y dashed of 0. Similarly L of y dashed 4 into s into capital Y of s minus small y of 0, and L of small y is capital Y of s. Laplace transformation of sine t is what? 1 upon a square plus 1. So we have taken the value of y0 equal to 0, y dashed 0 equal to 0. So this term and these terms are getting 0 only, right? So all these terms are getting 0. So we are having a square capital Ys plus 4s ys plus 3ys equal to 10 square plus 1. So we have taken a capital Ys common. We are getting a square plus 4s plus 3 equal to 10 upon a square plus 1. Now we are dividing both sides by a square plus 4s plus 3. So a square plus 4s plus 3 can be middle term factorized, and the factors will come as s plus 1 into s plus 3. So ultimately capital Y value is equals to 10 upon a square plus 1 into s plus 1 s plus 3. Now how to do the partial fraction for this kind of case? If you see, this will come as the third formula for the partial fraction. Here we are having two factors which are linear power are linear, and another factor which cannot be break. It is a non-breakable factor. Okay, so for this, how to do the partial fraction? First of all, we will deal with the linear factor term, that is a upon s plus 1 plus b upon s plus 3. What we have to do for this quadratic term, a square plus 1, since below we are having quadratic, so numerator will be linear, that is cs plus d upon a square plus 1. So always remember, if we are having the factors like this, say a square plus bs plus c, which cannot be breakable. So the partial fraction will contain like this type of term, as plus b upon a square plus bs plus c. Okay, this type of thing will going to come while you do the partial fraction. Now so how to get the values of a, b, c, d? Since already I have told you that partial fraction always identical, so whatever value you choose, you can choose and find out the value of a, b, c and d. But it is easy to substitute from the factors so that the calculation will be little bit easy. So by putting a is equal to -3, we are having the value of b as -1/2, sorry, and putting a is equal to -1, a equal to 5/2, putting a is equal to 0, we get the value of d equal to 1, putting a is equal to 1, we are getting the value of c as -2. Okay, now we are going to substitute all these values in the inverse Laplace transformation formula. So yt, that is coming as 5/2 by s plus 1, L inverse of -1/2 by s plus 3, L inverse of -2s plus 1 by a square plus 1. So 5/2 can be taken outside, we are having L inverse of 1 by s plus 1, -1/2 can be taken outside, we are having L inverse of 1 by s plus 3, -2 can be taken outside, here are two terms, so it will be s by s square plus 1 plus 1 by s square plus 1, so two terms are there. Okay, so -2 will be taken outside, it will come as L inverse of s by s square plus 1, it is coming from this term. Now second term, it will be 1 by s square plus 1, L inverse of this. So now from here it is coming as e power minus t, 1 by s plus 3 is e power minus 3t, and from here s upon s square plus 1 is cos t, and 1 by s square plus 1 is sin t. So this type of question you please practice. Now we are going to come to the final formulas. You can roughly go through the formulas. I think all of you know this, but before you apply the concept of the Laplace transformation, all these 8 formulas are needed, and these are very, very helpful. So with this, today's lecture I am going to close. Thank you all.